Hi all, my name is Alan George Phillip and I am an undergraduate research assistant in the Department of Mechanical Engineering at Wichita State University. My research is the capillary flow measurement of 3D printed metallic wick. My main role is to characterize different 3D printed metallic wicks and sometimes even furnace sintered copper wicks using something called a rate of rise test. So as you can see on the top right image here, you have the wick structure and there's a fluid inside the wick structure. When it's in contact with the hot area, the fluid evaporizes, and it expands over to the other sides. And once it's on the colder region, it condenses and forms the fluid, and the wicking capability of the wick structure allows it to move from the cold area back to the hot area. So there have been many different approaches to manufacturing the wick structures. Some examples are the furnace sintered wicks or axial groove wicks, screen wicks, template sintered, and composite wicks. All of these approaches have different limitations, such as the lack of control over the geometry, or low capillary pumping, or complex manufacturing, etc. So additively manufactured Wicks is a relatively new approach and hasn't been fully understood just yet. So doing my research, we can get a better understanding on the optimal pore geometries and pore networks, as well as the process parameters that corresponds to 3D printed metallic wick structures. So the main goal of this research is to manufacture an ideal wick structure, and these wick structures have two properties, which is a high permeability and high capillary pressure. But these are contrasting traits because high capillary pressure means smaller pore sizes, high permeability means bigger pore sizes, and so to achieve them both, we make a non-uniform pore size wick structure using a metallic 3D printer. So the 3D printed samples, basically there's two types that we're going to use. They are the lattice samples and the sintered samples. So the sintered samples basically focuses on the change in process parameters, whereas the lattice samples focus on the change in the pore geometries. And the working fluid that we're going to use is an FC72 fluid, which is basically a heat transfer fluid. It's very thermally and chemically stable fluid used in many electronic applications. So some of the keywords are, first one is porosity. It shows you the void space inside the porous media. And you can easily find it by comparing the mass of the wick structure with the fluid inside it and the mass of the wick structure without the fluid inside it. Another term is the effective capillary meniscus radius, and this is basically the curvature of the capillary meniscus. It can be approximated to find the effective pore radius and is represented by the below equation. Sigma here is the surface tension, rho is the density, sigma is the surface tension, and HEQ is the equilibrium height, which is the acceleration due to gravity. And permeability is this character K here, and it actually shows you the ability of porous media to allow fluids to pass through it, and it can be estimated using this ordinary differential equation. And yep, T here is time, and yep. So there's a relation between the height of the fluid inside the wick structure and the mass. It's given by this equation down here. A here is the cross-sectional area of the wick structure. So you have the previous equation, and if you make a small substitution for H, then you get the second equation. So this is the actual experimental test setup. So you have a glass tube, you have wick structure, and you have the working fluid. We just wait for 10 to 20 minutes before the fluid is fully saturated, and then you just slowly lower the wick structure into the working fluid, and you measure how fast the fluid rises up the wick structure. So we did the same thing. We started off with one of the 3D printed wicks. It's called the Lattice 5 sample, L5 sample, and the FC72 was chosen as the working fluid. And we lowered the sample into the working fluid, and we started measuring the fluid uptake through the wick structure using an optical camera. And we found out that it was very difficult to find the wetting front. It was very difficult to see the fluid go up. And it was even worse in the other 3D printed samples. So this was the best sample we had, and even that one proved to be difficult to work with in terms of an optical camera. So then we switched to an IR camera, and we were able to see something for the wetting front. If you see here, you have this dark area, which is, we assume, corresponds to the wetting front. But this is in an ambient setting, so there is no glass tube, and we don't have saturation, so that's the issue in this case. So yeah, this is a comparison between the optical and the IR, both in ambient condition. As you can see, they diverge at around 10 seconds, and we believe that's because it's not saturated and there's a good amount of evaporation happening. So we switched over to another setup where things are sealed. There's an IR filter here. However, we try to saturate it and seal it and remove evaporation, but there is still some small openings down there, and that made it very difficult to conduct these experiments. There is even fluid loss through that, so we gave up on that. And we started using a mass balance and measured the mass instead of visually finding the height. So we first measured the rate at which the evaporation takes place, and we got this plot here, and then we found the rate at which the fluid goes up the wick structure, and we plotted it on the right hand image down there. This was also in ambient conditions, so we had to minimize fluid evaporation, we had to seal the setup, and so on. So that's what we did. We put the setup on a mass balance, and we sealed it, or we attempt to seal it using a glass tube with a rubber base. We chose a cylindrical copper center wicks for now, and we found the evaporation again, and we got these two plots here. The evaporation rate was found to be something around 0.001 in both cases. So we tried it again over a much longer time interval. We tried it 3 different times, and we got a evaporation rate of negative 0.00133 gram per second. And we tried the rate of rise, the mass-based rate of rise on the cylindrical wick structure. There's two different types. There is a 550 micrometer particle diameter wick and 350 micrometer particle diameter wick. And we got the following graphs. As you can see, the blue one and the red one are two different trials, and they're not the exact same. So this is the problem we're facing right now. The experiments are not consistent for some reason, and we believe that's due to some fluid evaporation that's taking place somewhere. So currently, what we're trying to do, or the future work that we're going to do, is we're going to use rectangular copper center wicks, and these wicks have known properties that can be measured easily using optical rate of rise. So we're going to use the mass-based rate of rise on this rectangular wick structure, and we're going to do it over and over again using trial and error until we'll get a consistent way of measuring it, a consistent result. And once we get the consistent result, we'll apply it on the 3D printed wick structure. We use the mass-based rate of rise on the 3D printed wick structure, and this will provide us with valuable insights on the capillary performance associated with the various pore sizes as well as pore connectivity. And Acknowledgements to my advisor, Dr. Gisip Wang, and also Dr. Rajiv Nair. These are both professors in the Mechanical Engineering Department at Wichita State, and Munyandiri Ekbo, or Kelvin, is a graduate student who helped me with experiments using software and presentations. Also, Mohammed or Paim is a graduate student who helped me understand what's going on in the research. And also thanks to the Dean's Office for funding my research. So thank you very much, and I hope this helped you understand more about my research.